Okay, let's have one example for a rigid bar SDOF system. So since this is a rigid bar, there's no flexibility involved in this member. So we don't have to add the stiffness of this element to the stiffness of the spring using the principle of parallel and series uh, connections that I've discussed a while ago. So I would just like to solve this simple problem using two methods, and the first one is the equilibrium method. Okay, so the first thing you have to do is to take note of the coordinate of motion. So for this particular problem, the coordinate is actually vertically directed. So this is your y, and this bar is capable of vibrating back and forth or up and down here, so that your deflection curve, or simply your vibration curve, is represented by a straight line. Okay, so since the bar is rigid, this line is straight. And of course, taking the free body diagram of this bar, we have here a reaction at this point, and then we also have here a spring uh, reaction, which is Fs. And also, since it's a lump mass, there is a reverse effective force equivalent to the mass times the acceleration. Okay, so this is the acceleration is represented by y double dot, because this is a displacement. You take the second derivative of y, so that this becomes mass times acceleration, and this is concentrated at this point only. So for the uniformly distributed mass, the deflection curve will create a triangular, okay, inertia. Okay, so this is now your inertia force, which is varying from 0 at the support up to a maximum, okay, at the other end. Okay, so this is now the uh, inertia forces brought about by the movement of the rigid bar. Okay, so this is now equivalent to a resultant, okay, force located at 2/3. So this is located, okay, at 2/3 the length of the bar, and this is simply the area of the triangle, in which your value here, the maximum inertia force here, is simply equivalent to the mass multiplied by the acceleration. Okay, so this is simply m times y. uh, you have here a double dot. So for the area of this triangular uh, curve representing the inertia force, so this is simply 1/2 times the length times the height. Okay, so this is y double that. Okay, for the solution using the equivalent frame, or sorry, the equilibrium method, we simply take summation of force of moment, okay, about the reaction. Okay, so to take this as 0, we take moments at the reaction. Okay, so we have now your first force. Of course, your reaction becomes 0. So this is 1/2 m l y double dot multiplied by 2/3 L plus, okay, the spring Fs multiplied by, let's substitute the value of Fs. Okay, so note that Fs is simply equal to K of the spring multiplied by Y. Okay, so we can now substitute Ky multiplied by L plus M y double dot multiplied by. Okay, so this will now be simplified. You can cancel out 1L here, 1L there, and 1L there. So your equation is simplified. You can also cancel 2 and 2 there. So this becomes 1/3 of M L y double dot plus Ky plus My double dot equals 0. Okay, to make your equivalent system, so we are now solving the differential equation of motion. So we can combine these two since this is both acceleration. So we can factor out 1/3 m L plus capital M multiplied by y double dot plus Ky equals 0. Okay, so this is now your what you call your equivalent mass, M asterisk, and of course your K is your equivalent stiffness. And this is an example now of the differential equation of motion of a free undamped SDOF system.